Hello, my name is Rob Reynolds. Welcome to Business Calculus Section 1.6. Today we're going to continue our discussion on limits and specifically look at continuity. Continuity is if the function is continuous or not. We're also going to look at the greatest integer function, sometimes referred to as the step function, and then we'll look at some real-world problems. Again, continuous means that it's unbroken. There's no holes, no jumps, no gaps in the function. Seems like a pretty simple concept, but this really eluded mathematicians for many, many years, centuries, when they started talking about it. The precise definition seemed confusing to them. We'll see if we can try to clean this up for you. So it's discontinuous at a hole. It's discontinuous at a gap. And then this is discontinuous. So even though the function is defined, this is still discontinuous. This function is discontinuous because although the limit from the left is equal to the limit from the right, the function is not defined in the same spot. So there's really a checklist. It's a three-part checklist to check for continuity. And the first one is, yeah, the function just simply needs to exist. And I'll say, well, maybe the limit here is 4. I don't know what it is, but we'll just say the limit at c sub 3 could be some x value, goes up to 4. But not the limit. The function is defined. So in other words, there's a point. Let's call this 5. So now this is just f at 5 equals 4. Easier to look at. So we just have a point. Remember, this is f of x equaling y. So we have an x and y point right here. And so that's what the first checklist is. Yes, the function has to be defined at the points. We also need to check the limit. The limit at, well, I've defined it at 5, has to exist. Now remember, to check for limits, you really need to check the limit as x approaches from the left and the limit as x approaches from the right of this function. Well, I should have written, I don't know what this function is. Oh, I know, we can just write f of x in here. So the limit of this function as x approaches 5, we need to check the left and the right, and if they're the same, then the limit exists again. But it may not exist at 4. You can see the limit up here is at so we'll say the limit, remember, it's about the approach, not the destination, is at 7. So then step number 3 says rule number 1 has to equal rule number 2, and obviously it doesn't. Rule number 1 was a 4, and rule number 2 was a 7, and 4 doesn't equal 7. Therefore, it fails the checklist. So because, this is just explain it a little bit more, because f at x doesn't equal the limit, then it fails the test, not continuous. Again, for a function to have a limit that exists, we need to check the left and the right, and that's what this little notation is. The minus is the approach from the left, and the plus is the approach from the right. So here's your little checklist. It has to be defined, the limit has to exist, and then wherever it's defined, number 1, actually this number 2 has to equal number 1. They have to equal each other. If it's a polynomial, you could just say, hey, I'm done. All polynomials are continuous. Never discontinuous. There's no holes, gaps, jumps, undefined asymptotes. So you can see they're nice, smooth, continuous over the interval. Rational functions, on the other hand, have, which means they're some kind of a fraction, usually have variables in the denominator, and then of course we have undefined values like x can't be 0 because then you divide by 0. And in this case, you can see I've got a 0 at x can't be 1, and that causes a hole in the function. And over here, I've got a couple undefined values because this is, if I factor that denominator, what? X plus 1, x minus 1, the difference of 2 squares. So we have an undefined 2 vertical asymptotes here. So again, if I were to ask for continuity, is it continuous? In example A, you would say no, because x can't be 0, Either you could say everything up to 0 and then 0 to infinity, which is the way I think WebAssign will want your answer. Or you could, if you're just on a test, tell me all reals, but x can't be 0. That's kind of a shorthand way to do it. But I think if you're on the computer, they're going to want this notation. Here, everything but x can't be 1. So again, interval notation up to 1, and then sometimes they even put in union with 1 to infinity. The computer, if you're doing your online homework, will help you out with that. And then this one, believe it or not, there is no time that x squared is equal to negative 1, because you can't take this. So since it's never undefined, you would say it's defined everywhere from negative infinity to infinity. And again, these solutions are posted on Blackboard, and you're certainly welcome to go to Blackboard and print off the worksheet and follow along. So here's what that third function looked like. You might just want to pick up your graphing calculator and kind of look if it's continuous, but it's hard to see holes on your graphing calculator, so I would definitely check algebraically. If it does have a hole, it's called a removable, and the removable of the function oftentimes looks like a factor literally being removed from the function. So if you can remove the function or cancel out a factor and then rewrite it, then you know you have a hole. In this case, I have a hole at 1 comma something. We'll just call it f1. There's some y value. So whatever factor you're removing from the function, that creates a nice little hole, and that's what's very difficult to check on your graphing calculator. So that's why algebraically it's nicer to check. Sometimes another example of discontinuity is where you have a non-removable. So the last, if it's a factor that you can cancel, it's a removable. But a non-removable has a discontinuity, and that's usually called an asymptote. And there's the example where, well, x can't be 0, so that causes a discontinuous place. So here, you know that you can't take the square root of a negative number, so 3 minus x has to remain positive or greater than 0. So I'll add x to both sides and get 3 is greater than x, which of course you know is x has to be less than 3. You could write that in interval notation from negative infinity all the way up to 3, and it cannot include 3. If I could, if there was an equal sign underneath there, well, actually, I think there is an equal sign, because you can take the square root of 0. The square root of 0 is 0, so I think my definition is wrong. I'm going to add a 0, which means I change that parentheses to a bracket, which means I can include 3. Let's just check it. If I let x be 3, I'll get 3 minus 3, and the square root of 0 is 0, and therefore I found a point, 3 comma 0, and it's closed. So it is continuous. I mean, it's defined at 3. Good. They also used a bracket. They probably did it right correctly the first time, and there it is, a nice closed point. And you're certainly welcome to pick up your graphing calculator and check to see if you can graph it as well. Closed intervals, again, just mean I'm going to have some defined value that I have to, some range that I have to stay within. So I'm staying between some a and b value. So this function is closed because I can't throw in negative numbers. So this is saying, hey, just stay in that positive area for this graph. This graph is a little confusing because it kind of looks like that's an open circle, and I would just close dot there. I don't know, maybe that's 0 for the origin, 0, 0. I'm not really sure what the author wanted to go on there. This is called a piecewise function, and a piece of the function is defined between -1 and 2. Well, what does that function look like? Y equals 5 minus x. Let's graph that first. To do a piecewise function, I usually encourage students just to plug in. If x is -1, 5 minus a -1 is 6. And so I'll start there. At -1, 2, 3, 4, 5, 6. And it's a closed dot because it's equal to it. And another closed dot at 2. So if I let x be 2, I'll get 5 minus 2 and get 3. And I'll plot that point. 2, 3. And I recognize this as a boring line. And so I could draw on this entire line from here to here, but remember, it's not defined for all those values. It's only defined between -1 and 1. So instead of drawing in the entire line, I'm just going to draw in that line that connects it between -1 and 2. I'll continue the function. This is not a line. If you recognize your functions, this is a parabola, and it's shifted down 1 unit, so it's kind of here. And again, the parabola, the value of a is 1, so we know it goes over 1 up, 1 over 1 up, 1 up both sides. So it kind of looks like this. But again, it's not defined for all those values. It's only defined between -2 and 3. And so again, you might just want to consider plugging in a 2 here. So 2, well, let's get rid of this because we know we can't define it for all those values. It's only defined between 2 and, so let's get rid of this. There you go. And so it starts here 2, but 2 squared is 4 minus 1. So 2, 3. Oh, good. It picks up right there. It looks like an open dot, but it was closed up here, so we'll just keep it closed because there's no reason to put an open dot over a closed dot. The function at 2, 3 does exist from this top function. And then, so remember, I know the general shape of this, the general shape of this looks like this. I know the other point's got to be up here somewhere, and I don't really care about this side of the function. But visually looking at the function, I have to get rid of all of these small little dots. And I'll just erase because I don't want you to think that's part of the function. So if you plug in a 3 squared is 9, minus 1 is 8. So yeah, sure enough, it's way up here. And then, so it looks like this. I could even label this 3, 8. I could even label this -1, 6. So there's your closed interval function. It's just one function, even though I drew it in red and green. It's just one function defined between -1 and, well, really 3. And it's closed on the interval. I'm only looking at the function, this piecewise function between that closed interval. Oh, good. The author has something very similar. And again, they're using brackets because I can equal those values. I think these are just explanations of, so it's continuous. The greatest integer function, sometimes the step function, usually says all the values. So I asked, I don't know, notation for this keeps changing, but it's the greatest integer less than or equal to. I need the greatest value of x that is less than or equal to, excuse me, the greatest integer less than or equal to x. So if I were to ask, what's the greatest integer less than or equal to 1.6, you would say 1. And what's the greatest integer less than or equal to 1.2? It's still just 1. In fact, it's going to be 1 for all those values between 1 and 1.99999, everything up to 2. So that's what forms this closed dots on the left and an open dot on the right. And it's open because as soon as you hit 1, the greatest integer less than or equal to 1 is 1. And so that's what these examples are about, that if you're following along on your worksheet, you can fill these in. And just move those so you can see some solutions. Again, here's another picture of what that looks like. And they're saying just truncate, don't round. This is different than rounding. Truncating says this does not round to 4. Okay, I know, well, it does. 3.57 does round to 4, but that's the greatest integer symbol. And we're saying it just the greatest integer less than or equal to. So the practical application for you in business is sometimes we use this cost function. And again, we've got this greatest integer function in here. And we can see that any value less than 10,000, because 10,000 divided by 10,000 is 1, then x would have to be 10,000 before, because the greatest integer of 0.9 is still 0. So this is going to stay a 0 for all those, well, I'll just write it out. For all those values of x that are between 1 and 10,000, it's still going to be a 0 in there. So I could look at my cost function. 5,000, 1 plus this guy goes to 0. This whole thing is just a 0 for the first 10,000. And plus 3 times, well, we'll just leave that x. So the cost function for all all those values between 1 and 10,000 would just be 5,000 plus 3x. And that's a line that starts up at 5,000 and rise 3 and run 1. But then as soon as we hit over 10,000, the function is going to change a little bit. My cost function for the second 8-hour shift is going to look like, well, so let's see. This, when this doesn't equal 0 anymore, it's going to go to a 1 next. And it's going to do that between all values of 10,000 and 20,000. So when x is between 10,000 and 20,000, that greatest integer is going to be a 1. And then my cost function is going to be what? 5,001 plus 1 plus 3x, which is 10,000 plus 3x, which, what does that look like? Well, you start at 10,000, kind of do the same thing, but it's not here. It's actually, so can't do that. It's actually not defined because I drew it for this. So it's over here, kind of going like this. So then hopefully the author has completed this because my graph really sucked. So there's some explanation. Again, these PDFs, there it is, a little bit better. So we can't sell no books. So it's open on the left, closed on the right, open on the left, closed on the right. So this is a variation of that stepwise function. And then compound interest. I think you've seen this PERT formula before. PE to the RT for compound continuous. And, oops, that was weird. E to the RT. And then you've also seen P1 plus R over N to the NT for compound interest, where N is how it's being compounded, and if N equals 1, that's annually. If N equals 12, that's monthly. If N is 52, 52 weeks in a year, so that's being compounded weekly. If N is 365, and I know sometimes in business they use 360 days, but we're going to think this is a math class and use 365, then it's being compounded daily. And there's others, semi-annually is 2. So here we're looking at compound interest. Looks like the first payment we're going to deposit $10,000. Again, I'm just using this. That's the principal, 1 plus R over N to that NT. So I'll follow 10,001 plus the rate is 6%, which I'll write as 0.06. Compounded quarterly, there's 4 quarters in a year. I didn't talk about that on the last slide. Raised to the, so how long do I do this? Annual. So that means every year. So 1, and that gives me so, and then for the second time that, well, actually I suppose the first might be just the initial investment. That's the start value. Sometimes we let time be 0, but then the second, this might be the second, this might be the third. Let's see. But then it'd be 1 plus 0.06 for to the second, and then we continue. Let's see. Oh, so they did. They let the first just be 10,000. And yeah, and then you're letting this 4 be, I would have let the 4 be the fourth. They're saying, hey, yeah, they're off by 1, but I would have done the same thing. If you would have let T be the first year, we would have been fine. So again, a little bit of a greatest integer. If I sketch this graph, visually what's happening on this is, it looks like, again, a stepwise function. I hope you found this video helpful. There's a couple other examples. You're welcome to look at them. They're problem number 61 and 68 from the book. And I think I have worked out solutions for those. There's number 61 and I have worked out solutions here. 68, I have worked out solutions here. You're welcome to pause the video and work this out yourself, and email me if you have questions. Thanks.